Okay, welcome back to the second talk of this session. So it will be given by Siddhartha Mishra from the Seminar for Applied Mathematics at ETH Zurich. And his title is Physics-Informed Neural Networks for Approximating PDEs. Please, Sid.
Thank you very much, Patrick. And I would like to thank the organizers also for giving me this opportunity to talk here. So let me see. So we all know how powerful deep neural networks are and how powerful artificial intelligence is these days, means with all these, let's say, very successful applications. And we should remember that one of the, of course, a lot of it is attributed to supervised learning with deep neural networks. But one of the things that we should keep in mind is the role of big data. And by big data, I mean something like orders of tens of thousands or hundreds of thousands or millions of training samples. Now, in this meeting, we have had several talks where there is the impact of machine learning in scientific computing, particularly in the computations of PDEs, has been discussed. And my talk is also in this direction. And perhaps I'll start a bit off topic, not with pins, but with high dimensional parametric PDEs. So these are PDEs of this particular form. So here, this is a spatiotemporal operator, differential operator. U is a solution. It's a function of space. It's a function of time, and it could be a function of parameters. And in this case, it's the parameters that are high dimensional. So these parameters, for instance, could come from a probability space that parameterizes a random PDE, or they could come from a design space that parameterizes some design problem. In both these PDEs that I've shown here, the PDE is the same as the compressible Euler equations, 3D here and 2D here. Here we have some uncertain initial data, and we are interested in statistics of the solution. Here we want to design an airfoil to minimize drag or something like that. And the parameters correspond to the design parameters. So in many of these problems, the PDEs that you get are of this generic abstract form. Now, the issue is what you're interested is in computing the solution field as a function of parameters, or in computing observables, for instance, the lift, drag, quantities of interest, linear functionals as a function of parameters. And the issue, of course, is computational cost, because what you have to do is for many of these parameters, for instance, of hundreds or thousands of these design variables or of these uncertainty parameters, we need to compute so that we can get statistics or we can do design. So the issue is computational cost, because multiples, we have to call them multiple times. That's why these are called many query problems. And even an individual sample, an individual realization can be very expensive. Just to give you an idea of the scale that we're talking about. So this computation here is done with about 1,000 cells in each direction. So it's more than 10 billion degrees of freedom, the overall computation. And it's a very expensive simulation. It costs a lot on one of the most powerful supercomputers on Earth. But now what you're not interested is in a single realization, but what you're interested is in hundreds or thousands of these realizations. And then even for 500 of these simulations, the cost is prohibitively expensive. It's about $7,000 US. So you cannot do that. So one way you can overcome this is to design surrogates. And a very powerful class of surrogates are deep neural networks. So you want to approximate fields and observables with deep neural networks. And you've already heard talks yesterday and in the other parts of the conference where people have spoken about how these surrogates can be designed. But the bottom line is, at the end of the day, where even if you have very small networks, for instance, if your underlying function is an analytic function, you have small networks, but at the end of the day, you will get an error equation which looks something like this. So your total error scales something depending on the hypothesis space, the type of neural networks that you are considering, and 1 over the nth alpha power of the number of training samples. So even if this guy is of the order of 1, the point is that if you have random training points, then this alpha is at best a square root. You have some logarithmic corrections, but at best it's a square root. So as a consequence, you need quite a few samples in order to get reasonable results. For instance, to get 1% error, you need 10 to the power minus 2, you need 10,000 samples. And this represents a formidable challenge because you cannot generate 10,000 samples, right? Generating 10,000 samples, for instance, of this simulation is impossible. And for this simulation, it's going to be very expensive. So scientific computing is about learning in a data poor regime that is using moderate data, something like of the order of 100 or 1,000 samples in order to learn, because otherwise it's going to be very expensive. So one way this can be done, at least in the parameterized setting, is to replace random points by low discrepancy sequences, for instance, Sobol points or Halton points and so on. Then if you have sufficient regularity on your function, it scales, the error scales like 1 over n, the sampling error, or the generalization is error scales like 1 over n. And if you have even more regularity on your function, for instance, if it's a solution of elliptic and parabolic PDEs, like Chris Schwab spoke about yesterday, then you can do even better. For instance, you can have a quadratic decay. So by using these kind of tricks, low discrepancy sequences, multi-fidelity training, and so on, in this parameterized regime with moderate amounts of data, you can do rather realistic computations. Here are a couple of examples. In the first one, again, I'm going to learn the flow field for an airfoil with compressible flow, with compressible Euler equations. And the point is, with relatively small networks, my networks are of the order of 10,000 parameters, and with very few training points of the order of 100 points, 1,000 points. In both these cases, I get an error of about 1%, of about roughly 1%. So here I'm predicting the flow field with respect to the shape of the airfoil. And here I'm predicting the time series at different locations with respect to the earthquake, the initial earthquake, or parameters modeling the initial earthquake here. So this is earthquake generated tsunami. Here you're interested in the spatial distribution. Here you're interested in a time series. And you do this fairly accurately, but the main point is the following: that if I would have just used a traditional numerical simulation, finite volume methods in this case, it would have, even a very optimized method would cost me about 30 minutes in both cases, 30 to 60 minutes. Whereas the prediction here takes about 1/10 of a second. So at 1%, you are able to do this and you gain something like 4 orders of magnitude. So there is a lot of promise and a lot of potential. But remember, here I still needed about 100 to 1,000 points. Means this was done with more like 128 points. This was done with more like 900 points, 800 something, 872 points. So you're still around 1,000 data points. Now what happens is, as I said, supervised learning works with moderate amounts of data. And here we needed PDE solvers where there was a reasonable computational cost for a single solve. For instance, here this was about half an hour, reasonable computational cost for a single solve. But there are many situations where you don't have access to that. For instance, if you have a very complicated three-dimensional domain, it might be difficult to generate a grid. If you have some multi-scale, multi-physics system, or if you have PDEs with high space dimensions. We have written a bunch of these. In some cases, you have representation formulas, so you can generate data cheaply, but in many other cases, you cannot. The point is that you cannot even have 100 to 1,000 data samples. You might have 10 with some luck, or maybe 0. So in these kind of settings where data is not available, or maybe it's available as a part of experiments where it's expensive, you cannot use this sort of supervised learning framework that I just explained. Rather, one has to use something unsupervised or semi-supervised. And this is what, this is the sense in which I think of physics-informed neural networks. So physics-informed neural networks have been around since the 1990s. They were simply not called that. They had other names, but they were really resurrected and reincarnated by George Kaniadakis. He's going to talk today in the afternoon. So George and his collaborators, they reinvented them somehow or rediscovered them, and they called them as physics-informed neural networks. And the original paper is extremely successful. Today, there are hundreds of papers on PINs, and I'm sure that George is going to talk about some aspects of it, particularly in the computational sense. The rest of my talk, what I'm going to do is to convince you, or to, let's say, elaborate on possible mechanisms to explain why they work, when they work, and when these PINs may not work, right? So let me get started with this context. So let me start with a very, very simple example. Instead of working with an abstract PDE, I start with a very, very simple example. I have the standard plain vanilla heat equation in 1D, and I have some initial conditions, and I have 0 Dirichlet boundary conditions. Now, the traditional method is you put a grid and you put a finite, it's in 1D, so you put a finite difference scheme with some Crank-Nicolson time stepping. This is what we teach in numerical methods for PDE 101. I will consider a completely different method, okay? And what is the elements of my method? So I have my space-time here. So in the first element of my method is I throw a bunch of a cloud of random points on the initial data, on the initial line here, along the boundaries, and in the interior. So a cloud of random points, could be Sobol points also if I want, but just a point cloud, no grid. So once I have this point cloud, what I'm going to do is I'm going to approximate the solution of the PDE with a neural network. So the neural network in this case is parameterized by theta. It's a standard fully connected plain vanilla neural network. And as its inputs, it takes the spatial coordinate x and the temporal coordinate t. So at any of these points, I can evaluate this neural network. So of course, for an arbitrary theta, the neural network is not going to fit my initial data. So I want to mismatch along all these collocation points, or I want to reduce the mismatch with the initial data. I throw it into my loss function. The same on the boundary conditions. There are zero boundary conditions. There's no reason why for an arbitrary theta, u theta should be zero. So I want to again evaluate it along these points and throw it into the loss function, trying to minimize them. Okay, so this is, so you try to fit the initial and boundary data, which are given to you. But what about the interior of the domain? Now I don't know the solution I don't have access to the solution of the PDE in the interior of the domain. On the other hand, I do know what the PDE is. This is going to be the heat equation, which is written here. I know that this is, if I use a smooth activation function in particular, I know that I can evaluate derivatives of this neural network with respect to both space and time by just automatic differentiation, backpropagation, chain rule, whatever you call it. So at each of these points, up to machine precision, I can evaluate the time derivative and I can evaluate the second derivative in space. And I can evaluate at each of these blue points here, these random points here, so-called PDE residual. So I can evaluate this and I can also throw that into the loss function. So my claim is now by minimizing the mismatch with the initial and boundary data and by minimizing the PDE residual at each of these random points, I'm going to get a good approximation to the solution. So the method itself is very, very simple. And you can already see how it can scale to different situations. I don't need a grid. I can work with random points. So instead of taking 1 dimension, I could have taken 100 dimensions here, no problems. The PDE here is, as long as I can evaluate derivatives, I can take any PDE, so it can scale to nonlinear PDEs, very, very complicated PDEs. So it's very appealing in that sense, in terms of its flexibility, and that's why it's being so heavily used and so heavily cited. It's trivial to code. In fact, this is the entire code for evaluating the residual. A few lines, anyone can do it. So it's very, very good in that sense. But the question remains is, why should this work, right? All that I'm doing is I'm minimizing the pointwise residual and I'm fitting the initial and boundary data. Why should this lead to anything sensible, right? So the idea here is that, of course, my objective is to minimize the total error measured in some LP norm here. This is an abstract PDE. U theta is my neural network. So the idea is I want to minimize this error, but I don't have access to this error. I have no measurements of the data or of the solution in the interior of the domain. Remember that. On the other hand, I have access to the residual. So in practice, I'm sort of minimizing this population risk, but ideally, I would like to minimize this population risk, but in practice, I only have access to a quadrature, random points or Sobol points or some grid points, for instance. So by minimizing this training error, I want to control the error. So what is the source of errors and how we can relate these errors? This is sort of leads to the following questions. The first question is, of course, is there such an object? Is there a neural network which is somehow close to the PDE such that the residual here and the training error, these are small? If there is no, because this is what we're trying to minimize, right? So if these objects are not small, then this is there's no point in looking at this problem, right? So this is a basic existence result that we would like to have. But of course, in practice, even if such an object exists, it might not be feasible to find it during training. So then the question becomes, what we have access to is sort of the training loss or the, let's say, the residual error can, by observing a small residual, automatically imply that I get a small total error. So if I bound like this, then this is automatically answered. So the route through which I'm going to do this is we minimize the training loss. Does this imply that there is a small PDE residual? And by having a small PDE residual, do I minimize the total error? So these are the sort of questions. And these questions, at least a strategy was provided. There are different ways to answer these questions, but a strategy was provided in this paper, which is going to be published soon. And the idea is the following. So first is there a neural network which is close to the solution of the PDEs for which the residual is going to be small? Otherwise, it's redundant to search for this small residual. Now, it turns out that as long as your PDE is smooth, I'm not going to quantify sufficiently smooth at this general level, but let's say that we can evaluate this differential operator pointwise, the residual pointwise, then we know that if this, so look at this here, so this is your residual, but remember that we have an exact solution of the PDE, so I can substitute it here. This is a differential operator. This is a differential operator applied to different functions. And depending on how many derivatives are there, we can estimate it in some WSP, in some high order Sobolev norm. So as long as I would have been able to approximate my solution in a high order Sobolev norm, I could at least show that the pin residual, the residual itself, the pointwise residual is going to be small. So this forces us to look into high order approximation or approximation theory results for deep neural networks in high order Sobolev norms. And there are some results, not just by us, but by other groups. So existence can be guaranteed if I have a smooth solution and if I have approximation results in high order Sobolev norms. But remember, existence does not mean that I can actually find this neural network. So for that, I need to answer the reverse question, that if my residual is small, does it mean that the total error is going to be small? So it turns out that if I put sufficient conditions, and the sufficient condition, I define it as some sort of a coercivity. So the coercivity condition is written here. So remember that my PDE is in this abstract form. So F is my right-hand side or inputs. So if I change my inputs, does my solution change proportionately? It's some sort of a stability or a coercivity statement. Of course, it's conditional because this bound can depend on your underlying solution and on your underlying neural network. So if we have something like this, and I'll show you several examples where we have this, then the error bound is something like this. So this is my error, but because of, remember that U theta is a neural network. So remember that we have this coercivity and this du equal to F. So the residual comes in here. So as long as the coercivity is there, a small residual, and if this guy is proved to be bounded or it blows up at a certain speed, then we can show the total error is going to be small. So coercivity equals and hypothesis on your neural networks equals small errors. And finally, you have the training error because this is a population risk. We don't have access to this, but we can minimize by using some quadrature formulas or some standard statistical learning theory. So this is going to be the route through which I'm going to control the error. I'm going to say that the training error is small. If you have a small quadrature error, then the residual is going to be small. And if you have a coercive PDE, this implies that the total error is going to be small. So now this can be tried out for different PDEs. Let me go through a few of them at least. I don't have so much of time. The simplest examples are, of course, Kolmogorov PDEs. By no means are pins the only way to solve Kolmogorov PDEs, but it's a good place to sort of illustrate the concept. So these are Kolmogorov PDEs. You know about them, heat equation, Black-Scholes equation, and so on. And one of the things we'll track is that here the dimension can be very high. So in this case, we were able to rather precisely compute things, and we are able to, for instance, use, remember that the algorithm itself does not require any representation formula. No Feynman-Cox formula, no representation formula is necessary. All that I need is the form of the equations, but we do need a representation formula to prove, for instance, that there is no curse of dimensionality and so on. And we have been able to do that. The details are in this paper. The essential point here is that your total error, so there is also a computable upper bound. The total error scales somehow like the training error, which in turn scales like the square root of the residual. Okay, so this is roughly what the estimate tells us. And because it scales as the square root of the residual, we actually see this. So you have the total error here, which goes 3 orders of magnitude down. The training error goes 6 orders of magnitude down. So it really fits the theory in that sense. So here's an example. You can illustrate this computationally. You can solve 100-dimensional heat equation, 100-dimensional Black-Scholes equation, 100-dimensional Heston PDEs, all with small errors and without any supervising or any supervised learning at all. So no representation formulas are necessary. So this was more of a toy example, a linear PDE. But here is another example of a very important linear PDE which arises in applications, particularly in physics. It does not have 100 dimensions, but it can be 6 or 7 dimensions. So this is the radiative transfer equations. So you have the dimensions amount to time, space, angle, omega, 2-dimensional in 3D, and frequency, which is usually 1-dimensional. You have some non-locality. It's a sort of multi-physics PDE. You can do the theory the way I have just explained, but let's look at some numerical results here. So the point is we can solve a 6-dimensional problem. Here it's not 100 dimensions, 6-dimensional, but it's formidable. There is no representation formula, there is non-locality and so on. It takes us about 1 hour of training time on my GPU on my local computer, and the error is about 2%. And this is a physically realistic example which comes about in astrophysics. So you can really solve these PDEs for which there is difficult to generate supervised learning very, very quickly. You can do this for nonlinear PDEs. You can do it for Navier-Stokes. The bounds are all there. Again, what is important is that you need smoothness. Solutions of Navier-Stokes, at least in 2D, have sufficient smoothness, and you need some control on the vorticity. So these are similar assumptions to what you have, for instance, for finite element methods. And this does a good job in terms of, here is a upper bound, and you can really see that it tracks the upper bound quite well. So it really works in this setting. Of course, if the vorticity blows up, then there is no control, and there's no reason why this method should work, or any other method for that matter should work. It works for nonlinear dispersive PDEs like KdV equation, Benjamin-Ono, and so on. So this is a very interesting example. So you have solitons here. For instance, let's look at this. You have solitons. It's difficult to compute these objects, but they are smooth, right? The equation is nonlinear, but the final solution is smooth. So you can see that this is computed to less than 1% error, and this takes less than a minute. It's in a matter of seconds that you can do this computation. You can do fully nonlinear PDEs. So far, these were sort of semi-linear, quasi-linear PDEs. Now you can do fully nonlinear PDEs. For instance, Monge-Ampere equations, Hamilton-Jacobi-Bellman equations. I know that there are talks there. There are other methods to do this, not for the Monge-Ampere equation, but for the Hamilton-Jacobi-Bellman equation. Again, you can go many dimensions. You can go 20 dimensions with 1% error. And remember, the key point here is that these are mesh-free methods. So for instance, I want to solve the Monge-Ampere equation on a sphere with Dirichlet boundary conditions. And I just put a cloud of points on the boundary, random points on the boundary, and a bunch of random points in the interior. And it gives you 2% error. So no need to generate complicated grids. It's a grid-free method. When it works, it really works well in that sense. There is a twist here. You have to do some sort of L infinity training, because here the entire theory is that of viscosity solutions. It is in W1 infinity. So you cannot really work with the L2 setting. Sobolev with L2 type or L1 type of training. You have to do L infinity training. So it seems like it works in every case, right? So let me present a case where it does not work, right? So this is a viscous-Burgers equation, a very simple equation. We can prove similar estimates like what we did before. And now this coercivity is conditional on the L infinity norm of the gradient. If nu is a fixed quantity greater than 0, then the L infinity norm of the gradient is bounded. But what we're interested in is what happens as nu goes to 0. In that case, you get a scalar conservation law, the Burgers equation, implicit Burgers equation, and we know that shocks can be formed, and this quantity here should blow up like 1 over square root of nu. So in limit, it shouldn't work, and it does not work. If, as you can see, so for nu at 10 to the power minus 3, it works like a charm, but when nu is taken to be 0, it does not work. There is no, the error is very large. On the other hand, there is still nonlinear wave rarefactions, but in this case, you have control on the gradient. And because you have control on the gradient, you see that this still works in the limit. So there are places where it doesn't work, and this is exactly related to singularities, and when you don't have sufficient regularity to evaluate point-wise residuals. In that case, you can use a weak formulation for the residuals. There are various different weak formulations. The one that I like personally is where both the neural network as well as the test function are going to be neural networks. So in that case, you have maximizing over the test function, minimizing over the neural network. So you have an adversarial training like you have for GANs. And in that case, it did work. So you have to also put in the entropy conditions, but that's a detail. And it did work, and the error did go down from 20% or 23% to about 2%. It worked well, but this is still very preliminary work. Now I'll just take 1 minute or 2 minutes that I have and try to explain what happens. So remember that in all these examples, I'm solving a PDE for a problem, and I did not need any label data. In this case, data from the PDE itself. If there is small amounts of data, I said, particularly for parameterized PDEs, then there is better empirical performance. But in principle, you don't need any data. However, there are problems for PDEs where even the initial data and boundary conditions are not available. And these are typically inverse problems, right? Here, the data, measured data, is a part of the problems. And pins are a very powerful framework for inverse problems. So let me just try to explain that in my last couple of minutes. So here's an example of an inverse problem. This is a unique continuation or data assimilation problem. So D is the domain, the PDE holds in the whole domain, and you know that you know the PDE. What you don't know, for instance, are the boundary conditions. This can happen in many situations that you don't know the boundary conditions, yet you have some measurements. You have some measurements in the interior of the domain in what is called an observation domain. And you want to construct the solution over the whole domain, right? So this is an inverse problem, a data unique continuation problem. And in this case, what you do is, of course, you remember that we can use the PDE residual all over the domain, and we just augment it with this data residual. Instead of the initial boundary data or boundary data in this case, I simply put the data that is available to me and I minimize these things together, right? So in principle, the algorithm is trivial. It's just a small extension to the algorithm that you have. It works again with the same sort of theory that I have explained before. For instance, for the parabolic PDE, I don't have data at the initial boundary for the full initial line. I have some measurement points in the interior. And in this case, the coercivity comes from what is called a Kalaman estimate. These are very popular in observability or controllability theory, and we can leverage them to prove error estimates. And it also works well in practice. You see, even with 100-dimensional, of course, it's a synthetic problem, you can solve this inverse problem to 2% error. So there is no curse of dimensionality even for the inverse problem. And you can do more realistic problems, for instance, Stokes equation. I'm sure that George is going to talk about Navier-Stokes equation. Here you measure the velocity in this black points, and you want to reconstruct over the entire domain, both the velocity and the pressure. Again, we have a Kalaman estimate that gives us coercivity, and the error is very nicely controlled. With very few points, even for the pressure, there were no measurements of the pressure, you get about 3.5% error. So you can also do classical inverse problems, but I think I'm running out of time. So let me just summarize my results. So the main point here is that supervised learning works very well, particularly for parametric PDEs, but you need to make it work for small to moderate data. You need like 100 data points or something like that. If you are in a completely data-free regime or a very data-poor regime of 10 data points, then PINs are a good unsupervised learning framework. But of course, there are several caveats where they work. So in particular, if the PDE solutions are regular and if the PDEs are coercive, then I sort of suggested to you a method or a way in which they can work. And these conditions, thankfully, hold for many different linear and nonlinear PDEs, both for the forward problem and more importantly for the inverse problem. Consequently, of course, there are caveats. If you don't have enough regularity, then you need some weak formulations of pins, but these are also coming up these days. And finally, if you want to generalize beyond the class that you're looking at, you have to use pins for operator learning. But I think George Kaniarakis is going to talk about it later. And I am sort of out of time. So thank you very much for your attention. And my apologies for taking a couple of minutes extra.
Thanks very much, Sid, for this very interesting talk. Are there any questions?
Yeah, Mario is asking a question.
Okay, just
Mario.
go ahead. You
Hi,
can
Mario.
Just unmute yourself and you can ask the question.
You have to unmute yourself. I don't hear you.
You're still muted.
Okay, thanks for this very nice talk. Just a question, as you pronounce very much that this is mesh-free. So if you look at a PDE or in a complex geometry, or look at a PDE with very heterogeneous coefficients, then for the integration, in order to evaluate the residual, you need a quadrature formula which is accurate enough. So how do you deal with this?
This is a very good point. So you do need a quadrature formula, right? In principle, if you put a large number of random points, a very large number of random points, you should be able to remember that I can put as many random points as I want. Means no one stops me from that, right? Because I don't need to know the solution of random points. Of course, then the training becomes more expensive because you have a large number of random points. So in principle, a very large number of random points eventually will do the job. So you don't need a very accurate quadrature in that. But if you, I do agree that you do need some information, right? So I think more than the number of quadrature points, what will hit you is the sort of constants in your derivatives, right?
But if you draw a large number of points, this also means that your computational time explodes somehow.
Only the training. Well, yeah, It does scale with the, but you can parallelize, right? It's not like you can't parallelize. So you can really parallelize. So there are tricks to do that. But I agree that it's not a complete sort of, it's not completely free. You at least need a quadrature. But remember what you're competing against, right? So just imagine if you want to do
I completely agree. So don't.
So I agree that there is quadrature points, and a good choice of quadrature points is essential in reducing the computational cost. But in principle, you can take as many random points as you want. You can blow up the computational cost and still compute. So this is possible.
Thanks.
That's a very good point that you made.
Thanks. Are there more questions? Maybe let me ask just a short question here, just on the slide that you're showing right now. So you mentioned that you have an estimate how you go from the training error to the theoretical error, right?
Yeah.
But it's a statistical estimate. So the last error that you're showing here is an estimate, and there is uncertainty connected.
There is uncertainty there. There is uncertainty there, but this is very, very small amounts of uncertainty. I didn't even plot it, but I remember exactly the amount of uncertainty. This is a plus minus 0.1%. On the U, and maybe it's a little bit more on the pressure. But remember that observations here are noise free. If the observations were noisy, so just imagine that if I have noisy observations, then the error bars here might go up. So, and you can also track this through this estimate here. Of course, in a short talk, I cannot I cannot expand on the estimates, but it's a good point. Noisy observations will lead to more uncertainty in the total estimate.
Okay, so thanks again for this very interesting talk. And then in the interest of time, we move on to the
can I ask a question?
Yeah.
So you say you can solve Monge-Ampere on the sphere, but it's incredibly smooth on the sphere. Can you solve
I'm sorry, I'm not getting audio. Can you be a bit louder, please?
Can you hear me now?
Yes, loud and clear.
Sorry. You say you can solve Monge-Ampere on the sphere, but it's incredibly smooth solution on the sphere. It's very, very regular. Can you solve it on a more general two-dimensional domain where it isn't anything like it's regular?
Yes. So of course, this is a very good. I'm sure that I can, but I haven't done it. I'm sure. You know, all the constants here, these are upper bounds, right? So these are upper bounds, and these upper bounds take into account the derivatives that you have in your system, right? So I haven't tried Monge-Ampere on a very complicated sort of geometry, but this can.
I'm not asking for it on the square.
On a square?
Yeah.
Oh yeah, for sure. These are, where is the Monge-Ampere results? Blah, blah, blah. Okay, here. So all these results are on the unit, the unit cube in d dimensions. So of course, 2 dimensions. So it's 3-dimensional Monge-Ampere equation is solved to 0.1% on the cube.
Right. Okay. Fair enough.
So this works really, really well. The solution is, I agree that on sphere it's even smoother. Actually, on sphere the error was 2%, because here the quadrature error is probably not very good. No, this even in 20 dimensions, it's like 1%. You can argue that this is a smooth solution because this was a well-known test problem. So maybe that if there are rougher solutions, it will do worse for sure.
Okay, thank you.
Okay, I stopped my share.